everybody. Welcome. Pretty good turnout here. I hope you're not too sleepy after lunch. Today we're going to talk a little bit about some of the really future-looking things we're doing in the Kubernetes project. What we're going to show you today is only partly available today, and some of it's coming in the release that's about to happen. But hopefully you'll see some of the great work that the community is doing to handle these more advanced use cases that we're seeing these days. My name's John Belamaric. I'm from Google, and I've been involved in Kubernetes for maybe 7 or 8 years. But for the last year, I've been working on DRA, which was initiated by Patrick Oley from Intel, who's here in the third row, and Kevin Clues has done a ton of work on this as well, but many other contributors from the community. So we are, we're all in it together here. And with me?
Yeah, my name is Morten. I'm also from Google. I've been involved with the Kubernetes project for like a few years, a little bit on and off, and been working on DRA for the last 6 months, roughly.
All right, so let's see what we're talking about here as far as these problems. I mean, I think that the really simple way to put it is, as workloads get larger, when you're doing large training jobs or things like that, you're using lots of accelerators. That means lots of nodes. And of course, lots of any kind of machine means more probability for failure. So more failure points, more failures. And with some of these kind of coordinated mechanisms across nodes, the failure of one node can kind of impact all of the nodes involved in the job. So how can Kubernetes help manage those type of situations? To kind of illustrate the problems we're talking about, I'm going to use TPUs as an example, but a lot of these same problems apply also in GPU training issues, although they may solve the problems in different ways. We'll see a little bit of that later. But for now, for our illustration, we're going to assume we have 64 accelerators, TPUs they're called, but they're similar to GPUs. And there's 4 per node. And so we have 16 nodes for these particular jobs. Or rather, for this particular cluster in our example, and then we'll have several different jobs that are each using a portion of that cluster, but not the whole thing. When we allocate a set of, say, 16 TPUs, which means 4 nodes, we want a few things out of that allocation. We want compact placement. What does that mean? It means things that are close to each other. So in TPUs in particular, you have topological constraints, but even with GPUs, like you'd want them all out of the same rack, right? You know, ideally, because then they're only one hop away. Well, with GPUs, we have similar kind of things where there's wiring between the chips, and we'll see it in a minute, and we can create certain arrangements and certain topologies. We want to make sure that the pods land on nodes that are close to each other in some way. We also want, if we're doing multiple jobs that are grabbing, therefore, multiple nodes, and we launch them simultaneously, we don't want them to pollute each other's compact placement groups. So we want to have some way to atomically kind of partition those requests into the sets of nodes. And then we want a way to deal with failures that doesn't require you to wake up at 3 a.m. and go make changes to some pod spec somewhere. How does it work today? Well, this is the multi-node, this is kind of the hardware layer infrastructure in one of these multi-node TPU slices, we call them. And in this case, you're seeing 16 nodes. Each of those nodes has 4 TPUs, and they're interconnected with particular wiring that's programmable, but it's there's a hardware layer that's fixed. You can segment that then dynamically into these different partitions where you can consume 1 whole node at a time, you can consume 2 nodes at a time, you can consume 4 nodes at a time, 8 nodes at a time, 16 nodes at a time. And there's different ways or arrangements, topologies, by which you can do that. We're showing a certain set of them here to illustrate it. So how do we do this in Kubernetes today? Well, we'll label each of those. So if I go back a slide, you see the little dotted lines around each of those sets of nodes. We can associate a node label with each of those dotted lines. If we do that, and then we're going to put that node label on our say our job spec. So all the pods will be confined to those set of labeled nodes. If we do that, we probably want to do the partitioning in a way that they don't overlap. Otherwise, if two different users schedule two different jobs and they use label selectors that are overlapping, then they might actually take away a node that is needed for a different job. So what that means is, I guess, and we have it summarized in the next slide, is that we have to choose between kind of this static partitioning, which means we may not get full utilization if we have different jobs of different sizes trying to run, or we have to risk those kind of race conditions. We have to coordinate between two different job authors about which label selectors they choose, because it's not scheduled. It's sort of manually specified in the spec, and so the people have to talk to each other. Secondly, if there is a failure of a node, you have to kind of go and back out the job and change the label selector and reinitiate the job. So that's not really the kind of self-healing we expect from a Kubernetes solution. So let's kind of walk through what that looks like in a real use case. Here we have, we run a job. It needs a 4x4 slice, meaning 4 nodes by 4 TPUs. So we manually go into some spreadsheet or something and we say, oh, that's this label selector. And so we go and we set that node selector on our job, and the scheduler comes in and it starts scheduling these pods, and it's working pretty well and everybody's happy and it gets almost done, but then node 12 goes offline for some reason. I don't know, there's a kernel bug and it crashes. So what happens? We can't schedule that pod. Now we're stuck. It's just going to sit there forever unless we actually go in and we kill that job and we create a new job with we go in and manually pick a different 4x4 slice and a different node label or node selector, and we resubmit the job. The scheduler can't do it for us because that node selector is fixed in our spec. So what do we do about it? Well, one, we can use an over-the-top solution like Q, which is awesome. That's also one of, I work with a bunch of people who build Q, and so that can really help in these kind of situations. But we're also working on something called DRA, which you may have heard of in other contexts, and we're going to give you a crash course on it right now. But this dynamic resource allocation is a new resource request API in Kubernetes that, as I mentioned, Patrick and Kevin and others have been working on for quite some time. We're beta in 132, and the features that we're talking about here today are coming in 133. So Morten, why don't you take over here?
Yeah. So DRA, I guess I said a lot of people here probably heard about it, but we're going to do a quick intro here. It's essentially an API for requesting devices and making them available to pods and containers. You can think of it has 4 pods. The first is an API to describe devices. This is what is a resource slice API. And this gives nodes the possibility, makes it possible for node to say I have a NVIDIA GPU and it has 40 gigabytes of memory. The second part is an API for letting users request devices. So that's what we call a resource claim. And that might be I need 2 NVIDIA GPUs, each of which must have at least 30 gigabytes of memory. Part 3 is essentially the thing that brings those things together. it takes the available devices and the request in the form of the resource claims, and then allocates devices to satisfy claims. Finally, the fourth part is the kubelet API that actuates the decisions by the scheduler, so makes the devices available to pods and containers. So this is an example of the driver side. So you can see the array resource driver that then is a kubelet plugin that publishes one or more resource slices, which has a list of devices. And those then become available in the API server. The scheduler can see them. So that means that the scheduler understands what's available in the cluster. And this information is also available to the Kubernetes autoscaler, which means that it can take devices into consideration for autoscaling decisions, which is one of the big advantages of this latest iteration of the array. And then we have the sort of consumer side, which is the resource claim, which lets users specify a set of requests, which specifies like which type of device, how many, and through selectors, which typically are cell expressions, can specify like things like it needs at least 30 gigs of memory, or it needs a certain number of cores. These resource claims are then referenced by pods, and pods can reference multiple resource claims, or a resource claims can be referenced by multiple pods. In the latter case, all those pods will then share the devices that are allocated to that claim. We'll get back to that a little bit later. And yeah, the resource claim is used by the scheduler. The results of the decisions that the scheduler make is written into the resource claim status, and that is used by the kubelet to make those devices available to the containers. But to describe now, and in general, the simplest use case that is often used for the array is like the devices that are attached to individual nodes. But the array can also model devices that are accessible for multiple nodes. That could be through things like the network. And as Sean mentioned, in 133, there's a few useful features that are being added. The first one is what we call partitionable devices, which makes it possible to model devices that can be partitioned into smaller overlapping devices, like NVIDIA MIGS is an example of this. We're also adding device taints that makes it possible to taint devices, not nodes that is already available. And this makes it possible to automatically evict all pods that has a claim on a device. And by combining these features, we can then provide a array solution for multi-host accelerators. So yeah, let's look at what this looks like for how we model those devices. So this is the same set of TPUs and nodes as John showed earlier. And what we do is that we map slices. Each slice becomes a logical device. So, and each of those devices will then advertise their capacity. And capacity, in this example, is the number of TPUs. So in this example, like the 8x8 slice would be advertised as a device with 64 TPUs, and similar for the others. Each device will also have a node selector that defines which nodes is this device available at. And like if you look at let's say the 4x4 slice on the top left, it will have a node selector that selects node 1, 2, 5, and 6. And yeah, as we also notice, in this case, there are overlap. So a single device is a member of multiple devices. And the reason that we can do that is that the array understands the relationship between these devices. So in this example, if the 2x4 slice here is allocated, the array understands that the 4x4 and the two 2x2s that are formed by node 11 and 12 cannot be allocated. So the array allows the same underlying device to be advertised as part of multiple devices, but it makes sure that only a single of those devices can be allocated at the same time. Yeah, so if we look at how consuming these multi-host TPUs will look like, here's an example of a resource claim. And you can see that it uses the TPU device class, and it has a selector that essentially says we want a TPU where the number of TPUs equals to 16. And as we mentioned, each node has 4 TPUs. With 16 TPUs, that means we'll have 4 nodes. And that also means we need 4 pods. And in this example, all those pods will reference the same resource claim. So it's an example of multiple pods sharing the same resource claim. And that reference is sort of an example that is shown on the right. So if we look at how this allocation will happen, we have a resource claim that says, give me a device with 16 TPUs. In our cluster, we have 4 devices that satisfy that resource claim. And it's up to the scheduler to decide which one should be used. Today, the scheduler, or essentially the array scheduler plugin, does this with like a first fit. So it looks at what's available. The first time it finds something that works, it allocates that one. In the future, we're looking at implementing a scoring, which would allow it to implement sort of not the first fit, but a best fit, and best would then mean according to some criteria. But yeah, when the scheduler then decides on a device, it'll then do that as part of scheduling of the first pod. So the first time the scheduler sees a pod that references a resource claim, that's when it makes this decision. And then the scheduler will then select the device. The device has a node selector, as you mentioned earlier, and that will then tell the scheduler which nodes in the cluster those workloads can run on. And in this case, we see it selected the bottom left 4x4, and it decided to place the first worker pod on node 11. And this node selector then restricts the pods where any other pods referring the same resource claim can run. So this is sort of similar to what John described earlier with the device plugin. But in that case, the decision of which nodes the pods could run on was provided by the user through selectors on the pod. But now the scheduler gets that information from the device that it's selected. So this happens dynamically. And yeah, we see the first pods ends up on node 11, the other ones in a schedule queue, and they'll all get scheduled on the devices that belong to this device. And then the workload can run. Now, circling back to the example earlier, what happens now if node 12 turns out to fail? We end up in the same situation at first. The 4th pod cannot schedule, but with device taints that is being added in 1.3, the driver can now taint the device with a no execute effect. And what happens then is that all pods that references resource claims that allocated that device will automatically be evicted. So all those pods will go back into the pending state. They'll be picked up by the scheduler again. And the time of the first pod that the scheduler sees, it'll pick a new device, and all those pods will be scheduled on new nodes, and the workload can continue running. This is then obviously different from what you saw with the device plugin, where this required the user to actually go in and start changing.
You can stay asleep when this happens at 3 a.m.
Correct. There's a few open issues or things that we're still looking to improve in DRA. In the example now, I mentioned that the nodes or the pods end up on the right nodes. What the array does not guarantee today is that those 4 pods end up one on each node. In theory, they could all get scheduled on the same node. There are a few ways around this. You can make sure that, or request enough resources on that each pod requests enough resources that only one can fit on a node at a time, forcing the scheduler to place them on different ones. It's possible to use anti-affinity to force them onto different nodes. Or it's also possible to use a per pod claim for all TPUs on each node. But all of these are sort of increases the complexity a bit, and we're looking to simplify that. We talked about scoring, so making sure that we choose the best fit, not just the first fit. And we're also looking to support preemption, so a higher priority workload can preempt a lower priority one, so it gets to run and gets to sort of steal the device. And yeah. And John.
Thanks, Morten. Yes, so that's kind of the story of how we do that with TPUs. As I mentioned early on, GPUs, like especially when you look at something like the GB200, which has 72 GPUs, it's using DRA as well for managing and coordinating the allocation of and the configuration of the different compute domains and IMAX domains. Kevin is here from NVIDIA, and he can be happy to chat with you afterwards if you have any questions specifically on how we're doing that with the GPUs. And Patrick and Kevin have a talk tomorrow giving an update on what the working group responsible for DRA in the Kubernetes community has been doing. And that's another great talk to go to if you're interested in all of this. So there's a bunch more talks. This deck is up on the gray ones are already happened, I think. But this deck is up on the Schedule, and so if you download it, the PDF, you'll have links to the Schedule entries for all the different talks associated with DRA. So we're opening the floor to questions now. I think there's a mic here if anybody wants to line up. While we're waiting for people to line up, I'll mention 133 is not yet released. And so some of the things we're talking about here aren't available yet. And even when they are, they'll be alpha. But we think it's important for people to get a head start on what we're building. Yes, sir.
Last year in Paris, DRA felt a bit controversial or up in the air. It seems like it's much more stable now. Is that a good read, or?
Yes, absolutely. So out of Paris, we formed this working group along with another working group called Working Group Serving to try and address two of the biggest issues we are seeing around AI ML workloads. One was Kubernetes' relationship to the hardware. That's Working Group Device Management. And DRA was one of the, is basically the main thing we've been working on there. And we revised kind of the design to be more amenable to auto-scaling, and that's how we came where we are. We've done a ton of work in the last year and made a lot of progress.
And it seems like the design, as far as I understand anyway, meets everyone's kind of concerns that they had with competing approaches. It's kind of unified everything. Is that a good read, or?
I mean, it's not perfect, but nothing ever is, but I think people are pretty satisfied with it. There's a couple of, like if you look at the original use cases document for, like say the GPU use cases, there's a few that probably we will struggle to meet with this design. Very few, though, out of that list. There's also a bunch of additional things we're doing, I think, that weren't even in those original discussions. So, and now it's auto-scalable, right? So the data is there to drive scaling decisions in a way that it wasn't before.
Awesome. Thanks so much.
Hello. Thank you for the great presentation. Correct me if I'm wrong. What I see as a DRA, even though it says resource, it is one-on-one mapping to a device. So when you think about resources, it's much more than devices. It could be, say, between GPUs, there is a throughput, latency, power, all the different resource ingredients tied to each other. How are you going to address that in DRA? Thank you.
That's a great question. So today we don't manage standard resources, CPU, memory, huge pages, ephemeral disk, things like that. In DRA, that's managed as it's always been. DRA has been really focused on devices thus far. We do allow, we're working on a number of features. I don't think I have I don't have the list here of all the features we're working on, but if you come to, is it tomorrow, Patrick? Yeah. Tomorrow, there's the workgroup devices update meeting, and you'll see the list of things we're working on. And one of those is what we call consumable capacity, and it allows devices to publish capacity values the same way nodes publish capacity values, and then allows users to request those via a claim. And rather than, so today sharing is done by pointing multiple pods or containers at the same claim, which means it's a user-initiated sharing. And if we have consumable capacity, then for the types of devices that can do it, for example, NICs, doesn't work well for GPUs without like vGPU technology, but for NICs, you can do like, you could request, say, a 2 gigabit partition out of a 10 gigabit NIC, and we could let the platform schedule multiple unrelated workloads on top of that NIC and consume the capacity out of the NIC. So we're looking at doing those things. It doesn't get to the level of you're talking about where there's relationships between the resources. We don't really have we have some ways to handle that around constraining the set of devices you pick, but it's quite limited. So come to the workgroup update meeting, come to the Kubernetes community and join us and help us build that.
Hi, John. My name is Yuan Chen from NVIDIA. So we had some discussions and offline about how to handle the additional tolerations, right, for GPU 10s in GKE because, so can you comment on that? So the problem is, so for the ports request GPU resources to use DRA, right? How can we patch the
So
ports?
let me explain the issue. So if you're using device plugin, which is the traditional way of allocating devices, at least in GKE and probably in other clouds, whenever you create a node pool with GPUs or TPUs, we taint the nodes. And then if the user forgets to put a toleration on their pod, it would never schedule. So we actually have a webhook that goes, you're using GPUs. I'm going to add this toleration so that you can schedule. The problem with DRA is that the resource claims are not part of the pod. So we can't look at pod admission time and know just by looking at the pod. We can't even really load the resource claims that are referred to because it's an eventually consistent system. It doesn't have referential integrity, like it doesn't have to exist yet. And so how do we know to tolerate those workloads? So I can give you what we want to do from a long-term perspective. I haven't figured out the short-term perspective yet. But so SIG-Node has had a problem for a long time where, for example, if you use certain features that require a feature gate to be set on the kubelet, the scheduler has no visibility into that, and it could deliver your pod to a node that doesn't have that feature gate set, and the pod won't run. So this is not a new thing. This is a pattern throughout the system. So we're working with SIG-Node to build infrastructure so that just like taints and tolerations, which are sort of administratively controlled, we would have a transparent mechanism where nodes publish capabilities and the scheduler analyzes the pod spec and related resources and determines what capabilities are needed, transparent to the user, and then adds those, considers those mechanisms in the scheduling process. So this could be used for things like kubelet features, and it can be used to both attract and repel pods from certain sets of nodes. So that's our long-term solution. I don't know when that's going to happen, though.
So short-term may the request require a user to manually and tolerate it. Long-term solution will take some time, right?
Yeah, I think there's some things we could. I mean, you could build a controller rather than a webhook that actually waits for when the resource claim gets added that wasn't there at the time the pod was admitted and goes, but it gets pretty ugly. So short-term, maybe just the user. I think we're out of time, but Morten and I will be around here, so happy to answer any other questions afterward. Thank you.